Hello everyone and welcome to my talk on Beyond Asymptotic Complexity, comparing functional quantum linear solvers. I would like to start with a why. Solving systems of linear equations has been a core interest of quantum algorithmic development since the early 2000s. Many applications of quantum technologies rely on some version of a quantum linear solver, especially in the area of quantum machine learning. Nevertheless, quantum linear solvers, denoted here by QLS, assume full fault-tolerant quantum computers. So, we cannot benchmark them yet on real hardware. One prominent example is the HHL algorithm that shows an exponential improvement in the problem size over the classical best-known methods. But we don't obtain as much information as in the classical case because we still have to read out the state. Why do we call HHL functional and also other methods that I'm going to introduce functional? It's because they implement a matrix function of A, which approximates the matrix inverse A to the minus 1. I'm going to clarify next what A minus 1 are, but before that, I would like to take a brief look at the asymptotic complexities. In this work, we compared 4 functional quantum linear solvers: HHL, quantum linear solver based on Fourier polynomials, and 2 methods based on Chebyshev polynomials, namely QLS-Chebyshev and QLS-QSVT, where QSVT stands from quantum singular value transform. The parameters that appear in all of these methods are the number of variables n, the sparsity, where the sparsity is the maximum number of non-zero entries in every row or column. Kappa is the condition number and epsilon is the precision. The question is, how do we compare them and why can we compare them? We compare them using a technique called hybrid benchmarking that I'm going to elaborate a bit later in my talk. And the reason why we can compare them is because they share similar assumptions. So let's see what are the preliminaries for allowing us to make such a comparison. As said earlier, the methods share nearly identical assumptions about the problem setup and the oracle access. Let's see first the problem setup. We consider systems of linear equations of the form AX equal to B, where A is an invertible Hermitian matrix. And B is a complex vector. As conditions for quantum linear solvers, we have that A is disparse and well-conditioned. Which means that K, the condition number, is polylogarithmic in the matrix size. And as a reminder, the condition number is defined as the ratio between the largest eigenvalue of A and the smallest eigenvalue of A. So, it's very important to have these 2 aspects in mind, that A must be sparse and well-conditioned, and by sparse, I also mean that D is polylogarithmic in N. Now, the goal of a quantum linear solver is to output a state of the following form. Where X is a solution coming from the linear systems of equation, and X is a quantum state that is proportional to this solution. And X tilde is an epsilon approximation of x. So, by solving a system of linear equations using a quantum linear solver, we obtain a state x tilde that we would like to be epsilon close to the actual solution to the problem. Now, in order to prepare the matrix A, we need to assume access to two oracles. We have an oracle OF, where J is a column index and L is an index for the nth element in the column J. So we have an oracle taking an element at a certain column position and it brings it to this state where F returns the index of the nth non-zero element in column J. And we have another oracle, OA, where J and K are indices and Z is the value of the entry that we are accessing. And it brings us to the following state. Where this is the bitwise addition. Okay, so now we have the preliminaries. We need an invertible Hermitian matrix, a complex vector. The Hermitian matrix must be sparse and well conditioned. The goal is to solve the system of linear equations up to some approximation epsilon. And all of the linear solvers that we are interested in, they assume the same oracle access in order to prepare A. So what we did in this work was to actually call oracle calls to OF and OA. So we came up with some formulas telling us how many calls we need to have to these oracles together when we put them together. So now let's move on to hybrid benchmarking. The original idea of this method was introduced here, and our goal is to derive estimates to the number of calls to the oracles OA and OF. That our methods of interest are making. So HHL, QLS Fourier, QLS Chebyshev, and QLS QSVT. These estimates depend strongly on parameters such as sparsity, condition number, and precision. Hence, to assess their performance outside asymptotic regime is difficult. We record all these parameters classically by looking at the structure of the matrix A. Our goal is to answer the following question: which quantum linear solver has the lowest number of query calls for several real-world problems. And in order to do that, I want to present to you our methods. As said earlier, quantum linear solvers implement a matrix function of A, which is the approximation of A inverse. These approximation functions are sums over Hamiltonian simulation steps for HHL and QLS Fourier or Chebyshev polynomials of the first kind prepared with block encodings. Next, we are going to look at the HHL method and see how we can compute these query counts by taking a brief look at the method. HHL is the first quantum linear solver algorithm, and hence it's historically important. We continue by taking a look at a simplified version of the HHL algorithm, and we will see how we can compute query counts. We don't expect it to be competitive, but the reason why I'm presenting it now is that it's easier to follow and to understand the method we are using to do the benchmarking. Let's give an intuitive picture. Let U, J, be the eigenstate of A. And lambda J, the corresponding eigenvalues. Where J goes from 1 to n. We assume that T0 lambda J equals to some 2 pi tau J, where these taus are just some integers. Going from 0 to some big T minus 1, and I'm going to clarify later what this T is. Furthermore, the eigenvalues lambda J, they are within this interval. For more details, I'm referring the reader to the original HHL paper. From this, we can see that tau J is larger than T0 over 2 pi over kappa, but is also smaller than T0 over 2 pi. So what I did, I just looked at the ends of this interval and I plugged them in here. The HHL algorithm starts with preparing the state B with some oracle PB. This is not of interest to us because it's more expensive to prepare the matrix A. So we're neglecting this part. So as we said, HHL starts with preparing the state B, and then it's applying quantum phase estimation with precision T. And U is just the exponential of E T0 over T. This is done in 3 steps. The first one, we prepare an ancilla state of dimension T. in a uniform superposition. We call this clock register. Then we apply the operator U, which has a control on the clock register. In the end, the QFT inverse is applied, taking the state to something of the following form. So these are the components of B in the eigenbasis of A, and these are the eigenvalues of A. So we can conclude that tau has been taken to some constant. To perform such a transformation should be enough for HHL, but this is not unitary. And it cannot be implemented directly. Hence, the HHL algorithm authors introduced an additional ancilla qubit in the state 0. And then they perform a conditional rotation of the clock state. Where the rotation has the following form. So theta satisfies the following relation. Sin of theta over 2 must be equal to this constant for tau larger than T0 over 4 pi kappa, and 0 otherwise, since lambda j is larger than 1 over kappa. Therefore, C must be picked such that the right-hand side is smaller than 1, meaning that C should be T0 over 4 pi kappa. Now, going back, we perform this rotation, we undo the quantum phase estimation, and trace again the clock register. Let's write these steps down. So we said that we perform the rotation R, undo the quantum phase estimation, and trace away the clock register. So after these 3 steps, we end up with a state of the form beta j uj times this. Where, don't forget that this C is T0 over 4 pi k. Now, the idea is that we measure the flag ancilla, and if the result is 1, we obtain the state that we were interested in, but if the result is 0, then the algorithm failed. The success probability is where I already replaced the constant c with T0k over 4 pi. And we have beta j tau j both squared. Now, in order to get our estimation, let's recall that tau j must be smaller than T0 over 2 pi. Hence, a lower bound on this probability is 1 over 4 k squared. And this can be boosted to 1 using quantum amplitude amplification, or some version of quantum amplitude amplification. Now, the reason why we did this is to actually find out this lower bound on the success probability, and to know the fact that we can boost it to 1 by using some version of quantum amplitude amplification. Going back to step 2, we see that this unitary is actually some version of Hamiltonian simulation. Why am I saying this? I'm saying this because the matrix A can be seen as a Hamiltonian. And by using different techniques, one can implement a Hamiltonian simulation method. Or one can implement this via Hamiltonian simulation, better said. And for Hamiltonian simulation, you can pick your favorite method. There are plenty out there. But what we used in our paper is actually qubitization. So my point is that at the end of the day, the cost of HHL for the queries is that it's made up of the cost of this qubitization method together with the cost of quantum amplitude amplification. So what I'm trying to say is the following. Lemma 3 in our paper, we are summarizing the query costs of the HHL method. And they are given by the two components that I mentioned earlier. So we have that the cost of HHL is given by 2 times the quantum amplitude amplification overhead times the query cost of implementing the Hamiltonian simulation method that we said that it's qubitization in our case. This 2 comes from the fact that the unitary U that is hidden here has to be implemented twice. What I mean by this is that we implement U and then U transposed. So this is the number of queries to the oracles OF and OA. Okay, but where is the success probability? Well, don't forget that the success probability is hidden here in the cost of implementing the quantum amplitude amplification. And the form of the success probability can be found in lemma 2, while this one can be found in lemma 1 in our paper. As said earlier, in our case, the probability of success was 1 over 4 kappa squared. This success probability is not the same for all the linear solvers, and that's the reason why it's important to look at all of them and determine what is its value. So what I presented here, it's a simplified version of the HHL method, but what we actually did in the paper, after looking at the simplified version, we took into account the real version, or more realistic version, where the quantum phase estimation doesn't start in an equal superposition. But this doesn't change the results that I just presented. Namely, it doesn't change this number of queries that we make to the two oracles. What is actually very important, I want to make some distinction about this probability. In order to run the algorithm, we don't need to know the success probability P. But in order to perform the hybrid benchmarking, and more exactly in order to compute this quantum amplitude amplification overhead, then we need to know a lower bound on the actual success probability. Because otherwise we simply cannot collect the data, and then we cannot implement this method. So for the interested reader, I would recommend you to go to the Appendix C where we discuss HHL, and also to go through Lemma 9 and Lemma 10 in order to understand how exactly things are working and how we obtained our results. But even more important would be to go through the cubitization section and to the quantum amplitude amplification sections. In the following, I'm going to state the other lemmas for the other methods, and then we are going to see the results. So we have lemma 4, which gives us the cost of the quantum linear solver based on Fourier polynomials. And the query cost is similar. We have the cost of quantum amplitude amplification times the query cost of the Hamiltonian simulation method. See, it's already a factor 2 better, but also we have a different success probability for the quantum amplitude amplification method. In this case, it's 1 over alpha, and alpha has quite a complicated form. So I'm going to give you the equation just for reference. Where there are a bunch of parameters that I didn't introduce except the condition number, but you can find their definitions in the lemma 4. So what I find very important is that you are aware that the structural blocks of these two methods are similar, but the success probability for the quantum amplitude amplification differs with the method. So it's not just this factor 2 missing, it's the fact that there is a different success probability. Then we have lemma 5, in which we have the quantum linear solver based on Chebyshev polynomials. And the cost looks something like this. The query cost of the QLS Chebyshev is given by 8 times sum G0 and the quantum amplitude amplification overhead. Where again, here we have another different probability. I will name it here 1 over gamma squared, because I don't want you to confuse it with the alpha that was before, but in the paper it's denoted as well as alpha. And this G0 also is just a notation that hidden. And this G0 is just a notation in which are hidden a lot of terms like the sparsity, the condition number, and so on and so forth. So I am referring you again to the paper for the complete form. In the end, we have lemma 6, the QLS QSVD, so quantum singular value transformation. And the cost has the following form. Okay, so this is the form that the query quels for the QLS QSVT method has. And within this form, so these are some functions, this n rect and n 1 over x. Again, here we have another success probability, 1 minus epsilon over 2 kappa, everything squared. So at the end of the day, I would say that we were really diving deeply into finding some lower bounds on the success probability, but it's not only that. So we actually went beyond asymptotic complexities. We tried to find all the terms, all the prefactors that are actually there, because when we have them, we can record the data that we need classically, and we just plug it in within our bounds. And when we do so, we can actually give some estimate saying, hey, look, HHL for this type of problems takes this many queries, while QLS-QSVT takes this many queries. So we are giving some pragmatical results. And now let's look at what we actually benchmarked. In our first benchmark set, we looked at self-generated random instances. And we compared the four methods. So we have HHL here with green, QLS Fourier, Chebyshev, and QLS QSVT. We made sure that our instances are well conditioned and sparse. Here on the right hand side, we were showing the number of query calls to the oracles OA and OF. And as you can see, HHL is not the best performing, having up to 10 to the 18 queries, while the situation improves. So QLS Fourier is having even less queries, QLS Chebyshev even less, and QLS QSVT has even up to 10 to the 4 queries. So this is quite an improvement from one method to the other. Therefore, for our benchmark instances, we decided to neglect HHL, because these were the instances where all algorithms could have shown their strengths. And since HHL didn't, we decided to simply discard it for the next benchmarks. Next step, we looked at real-world problems, but we filtered them. So from the real-world instances, we picked only the ones that are suitable for these linear solvers, and as I kept saying during this talk, we took the ones that are well-conditioned and sparse. And we observed consistent results with what we saw earlier, namely that QLS Chebyshev and QLS QSVT are the best performing methods. In the end, we also generated Poisson equations in 1, 2, and 3 dimensions, and the results are still consistent with what we saw earlier. So in the end, I could say that our motivation was to benchmark the quantum linear solvers on instances of practical interest without having access to quantum computers, to just use these tools that were already there and to try to put them into practicality. We think it would be really interesting to extend our method to adiabatic quantum linear solvers, since to my current knowledge, those are the best quantum linear solvers out there. Thank you very much for listening to my talk.